Thank you so much to the organizers for having me and for putting on such a nice conference. And I want to tell you about combinatorics of boundary algebras. And in particular, one thing I want to tell you about is what a boundary algebra is and how it relates nicely to the combinatorics of matroids and more specifically of positroids. I also want to tell you a little bit about positroids and some of the exciting stuff that I've been able to do with my co-author Jonah, who's at the University of Kentucky as a graduate student. And let me get first to positroids. So positroids are realizable matroids. They're a special type of realizable matroid which can be realized by a matrix with all non-negative minors. So let me give, by example. So here is a 2x4 matrix. The maximal minors, I write them out. Here I compute them with the index here giving you the columns. So P12 is the minor in columns 1 and 2. This identity matrix has minor 1. P13 is the minor in column 1 and column 3. It's like a 1, 0, 0, 2 matrix. Its determinant is 2. And you compute all 6 maximal minors, and we see that they're all non-negative. So from this, we get that the matroid with bases 1, 2, 1, 3, 1, 4, 2, 4, 3, 4, these are the non-zero maximal minors, is actually a positroid. So it's a special type of realizable matroid. And let me just give one thing that will justify why this may be a reasonable thing to do. There's a number which I hope to give a few more of throughout the talk. But realizable matroids give us a stratification of the Grassmannian. So every point in the Grassmannian, that is every k-plane in R to the n, gives us a matroid. And if we look at all the points in the Grassmannian which give us the same matroid and call that a stratum, then these strata can be as complicated as any algebraic variety. They get like arbitrarily bad. And this is a result of Nev's universality theorem. If instead we restrict to the positroid version of this, so look at the non-negative Grassmannian, by which I mean the subset of the Grassmannian where exactly all these minors are non-negative when you take your linear space and view it as the row span of a matrix, and insist that this matrix have all non-negative minors, we can play the same game and do a stratification by positroids, and this is nice. We get a regular CW structure, and in particular, the strata are all balls. So this kind of fixes our topological problem. Another motivation which came up on Monday in Peter's talk and then again in Jose's talk, there was this checklist of duals, minors, and cryptomorphisms, and these are in fact dual closed, minor closed, and I'm going to give some nice cryptomorphisms that describe them very combinatorially. And here's, I guess the first one. Positroids are in bijection with decorated permutations. These are permutations which I'm writing in one-line notation. And the decorated means that when I have fixed points, I either give them an underbar or an overbar. So I decorate my fixed points. So this one has 2 fixed points at 2 and 6, and I've given one the underbar and one the overbar. Now, in this talk, I'm really only going to be talking about loopless and co-loopless positroids. And the fixed points exactly tell you the loops and the co-loops. One decoration's a loop, and the other decoration's a co-loop. So for our purposes, we're really just going to be looking at permutations, like proper permutations. And I'm going to represent them primarily in 2 ways. One is going to be in this one-line notation, and the other is going to be as a directed graph with in degree and out degree 1 at each vertex. So these, 1 goes to 4, 2 goes to 5, 3 goes to 2, 4 goes to 1, and 5 goes to 3 in this picture. And that's exactly the permutation I have down here. Okay, so where do the boundary algebras come in? That's the thing in the title of the talk. So these come in from studying certain algebraic structures. And it all starts from positroid varieties. So a positroid variety is the Zariski closure of the positroid stratum of some positroid of rank k on n elements in the Grassmannian of k-planes in R to the n. So the positroid stratum is a collection of points in the non-negative Grassmannian. And so I just want to take the smallest subvariety of the Grassmannian which contains that set. And that is what we call a positroid variety. And positroid varieties carry this thing called a cluster algebra structure, which is a nice algebraic structure which is shared by a lot of combinatorics adjacent varieties like the Grassmannians and the flag varieties. I'm not going to tell you exactly what it is, but they are nice and they are common to these varieties that combinatorialists might care about, and they are themselves quite combinatorial. They have a very rich structure where you can start drawing trees and graphs and stuff, and that'll help you understand your cluster algebra. But whatever it is, we can do something called categorification to it. So this is a process by which we study it by using a category of modules. And in this case, the right thing to do is to look at some particular modules over algebras called boundary algebras. So we start from positroids. Each positroid gives us a variety called the positroid variety. Positroid variety has a nice structure called a cluster structure. And if I want to get insight into this cluster structure, I'm going to look at modules over the boundary algebra. And that's the algebra I want to tell you a little bit about today. Just a little bit of history on it. It was first studied for the full Grassmannian. So the full Grassmannian is a positroid variety. It's the positroid variety for the uniform matroid, which in particular is a positroid. So this was done by Jensen, King, and Su, and Bauer, King, Marsh, and was then generalized to all positroid varieties by Matt Pressland. And this is something that has been fruitful. So for example, it's been used to prove that two a priori different cluster algebra structures on positroid varieties are actually essentially the same. The technical word is that they quasi-coincide, but up to some equivalence, they are the same. So my main goal for today is to give a combinatorial characterization of boundary algebras, to tell you what they are in purely combinatorial terms. So to bridge the gaps from positroid to boundary algebra, I'm going to need to introduce these things called Playbook graphs. This is also something which, if you are careful enough, I'm not going to be quite careful enough in this slide, but you can describe a cryptomorphism between these Playbook graphs up to some moves with positroids. But what are they? They are planar bicolored graphs. They're undirected graphs embedded in a disk where each interior vertex is either filled or empty. Okay, and how do we get from a Playbook graph to a positroid? Well, I'm thinking my positroids as permutations, so the real question is how do I get from a Playbook graph to a permutation? And the answer is what we call the rules of the road. So we're going to have a little sign at every dark vertex, which tells us to turn right, and a little sign at every empty vertex, which tells us to turn left. So if I start on my trip from vertex 4, I come to this empty vertex, I turn left. I come to this filled vertex, I turn right. And this other empty vertex, I turn left again. So the trip from 4 takes me to 1. So my fourth entry in my permutation is 1. And I do this starting at every vertex, and it does give me a permutation. So for example, if I were to start at 2, I come down, I turn right, left, and right, and that takes me to 5. You do this for every vertex, and you get a permutation. So that's how you get from Playbook graphs to positroids. Now, I want to take myself from Playbook graphs to boundary algebras. And the way to do that is to do a different construction to my Playbook graph. This is the dual quiver. So I draw a quiver as a directed graph, and I draw a dual graph to my Playbook graph. I put a vertex in each face, and then I direct the edges such that the empty vertex is always to the right and the filled vertex is always to the left. So given a positroid, I've got these Playbook graphs that correspond to them, and each Playbook graph gives me a quiver. Now, there could be multiple Playbook graphs with the same trip permutation, so there's some redundancy here. And these different Playbook graphs might give me different quivers. So for a positroid, I really get a collection of quivers. And there's some work of Postnikov which shows that, that this collection is well behaved. They're all mutation equivalent, whatever that means. But for our purposes, what I really need to know is that corresponding to a positroid, I also have a collection of quivers. And that's going to allow me to construct the boundary algebra. So I'm going to give kind of the construction of the boundary algebra that exists in the literature. The details are not going to be super important. What I really want to emphasize is that there's a lot of steps. But we start, the first step is to construct this quiver, and it doesn't matter which one. We can start with any quiver. It's going to give us the same result in the end. And from here, we're going to do 3 kind of little constructions. The first is the path algebra. This is the algebra on this directed graph where the elements are finite paths, and the operation is concatenation. So here are 3 elements of my path algebra on this quiver in green, orange, and blue. And if I want to multiply the orange and the blue together, well, I'll just get the green path here, which is the 2 of them stuck together. So this is the path algebra. Now we're going to take a quotient of the path algebra. So it's a property of these quivers that are constructed from Playbook graphs, which is not too hard to verify, that every internal edge is contained in 2 oriented cycles. So what we're going to do is we are going to identify, in this picture, the orange and the blue, the parts of those 2 cycles that don't include E. So this is some quiver, this is some quotient of our path algebra. We're identifying certain paths. And finally, we're going to take the boundary algebra, which is a subalgebra of our dimer algebra, of our quotient. And it's given by taking only those paths with both start and end at the boundary. And that's where the boundary in boundary algebra comes from. Okay, so we've got a subalgebra of a quotient of a path algebra. All right, so that's a bit of a pain to get through. So one thing that's nice is that we can do a little bit better. So from work of my co-author Jonah and his advisor Christina Staryenko, we have a description of boundary algebras as a quotient of a path algebra. So we can get rid of that subalgebra step. But it's a different quiver. So, okay, what is our boundary algebra? It's the path algebra on some quiver Q pi circle, mod C, which is some operation of an ideal I pi circle. Where Q pi circle is a quiver on the vertices 1 through n, with arrows between adjacent vertices. And there's some other arrows. I'm going to tell you later how we get them, but some other arrows which somehow come from the boundary algebra. So if we start with the boundary algebra, the quiver I was using an example before, we end up with this quiver Q pi circ. We also have this I pi circ, which is an ideal. Again, I'm going to say a little bit more in a second. But what I do want to mention here is this C operation, which we call cancellative closure. And this is an operation which gives us the smallest ideal containing I pi circ, such that if we have an arrow of the quiver and an element of the path algebra, we can basically divide out by the arrow. So if we have arrow times element of the path algebra, PQ is in the closure if and only if Q is in the closure, and you can also divide on the right. So you can divide on the right and the left by individual by individual arrows in our quiver. And, you know, I don't have a good intuition for what this is, and in general, it's difficult to kind of compute how this works. So one big thing that we're going to do is we're going to give a new description of boundary algebras which gets rid of this cancellative closure operation and just gives a much more direct combinatorial description of what's going on, because this doesn't really tell you exactly what the relations are in your boundary algebra. So, okay, I need to tell you a little bit more about what this ideal is. It's determined from some combinatorial data. You can determine it from those other arrows of Q pi circ. So I said Q pi circ is these adjacent arrows plus some other ones. So I haven't told you what those other arrows yet. We're going to get to that in a second. But to figure out the ideal, you need whatever those arrows are. You need a pair of positive integers attached to each of those arrows, which we call its relation numbers, and some positive integer k. And I claim that we can get all this data from the permutation directly. So let me show you how that works. But before I show you how it works, let me show you how we're going to keep track of all this information. We're going to display it in a directed graph again on n vertices. And basically, we're going to just like write down what we need. So I don't need the arrows that are adjacent because they show up in every of these quivers Q pi circ. So I really only need the arrows between non-adjacent vertices. And then for each one, I have this pair of positive integers. So I'll just go ahead and write it in on the graph next to the arrow. And I'll keep track of the integer k somewhere. Okay, so that's how I want to think about the data that determines my ideal. And we'll call this a realizable boundary chart. So let me tell you now how we determine what these other arrows are, how we determine what the positive integers are, and how we determine what k is. Because I claim you can do it directly from the permutation. Let me back that up. So first question is, what are the arrows? Where do we add an arrow? What we should do is we should overlay our boundary chart and our permutation graphs. Remember, I'm thinking of my permutations as directed graphs with in degree and out degree 1 at each vertex. And if I want to know if I add an arrow, like I have this arrow from 1 to 3, how do I know I have an arrow from 1 to 3? In my permutation graph on both the right and the left, I have arrows that are anti-parallel to this black arrow and span from its head to its tail. So on the right and the left, so this purple 3 is right next to the head, this purple 2 is right next to the tail, and I've got an anti-parallel arrow which lies to the left of my black arrow. Now there's a lot of arrows going on, so I'm going to try to say arrow when I mean the black arrows and strands when I mean the purple arrows, just to keep track of them. So let's look at a slightly more involved example. Now I'm going to look at the black arrow from 10 to 1. On the right, I've got these 2 red strands, which do go from the head of the black arrow to its tail, and they cross each other. And they're both anti-parallel to my black arrow. On the left, I also have 2 arrows which are anti-parallel. Okay, they cross at a point, but that's good enough for me. So they touch at a point. And they span from its head to its tail on the left. So that's kind of how I test if I have an arrow or not. And then I also need these 2 numbers. And these 2 numbers are just counting how many anti-parallel arrows there are on the left and on the right. So I have a 1 on the right here, and that corresponds to the fact that I have exactly 1 purple strand, which is anti-parallel to the arrow, and lies on its right. Similarly, I have a 1 on the left because I have exactly one strand which lies to the left of my arrow and is anti-parallel. In the more complicated example, the 2 on the left is because I have these 2 strands now which lie to the left of my arrow and are anti-parallel. And the 4, okay, I didn't draw all 4 of them before because I didn't really need all 4 of them before. I only needed 2 to show that I have this crossing pair. But I actually have 4 arrows which are anti-parallel to my black arrow, 4 strands which are anti-parallel to my black arrow. And so that's where this 4 on the right comes from. Okay, so it's not like the easiest construction in the world, but you can determine all this information from the permutation. And then k comes actually from each pair of arrows. They satisfy this relation where x is that left number and y is that right number. They're not independent of each other. They're determined up to the reach of the arrow, meaning how far it goes, like how many steps it goes clockwise. Okay. And equivalently, maybe a more easy way to get k, it's the number of exceedances of pi, which means the number of I such that pi of I exceeds I. So pi of 1 is 4, which is more than 1. Pi of 2 is 5, which is more than 2. So I've got 2 exceedances. The rest are not exceedances. Here, the first 5 values are bigger than 1 through 5 respectively, whereas the rest are not bigger than their position. So you only have 5 exceedances. Okay. So this tells us how to determine all this information for a realizable boundary chart. I want to make a definition now more broadly. I can kind of imagine something, this sort of combinatorial data that doesn't come from a boundary algebra. So a boundary chart is going to be a directed graph on n vertices with no arrows between adjacent vertices and with 2 integers associated to each arrow which satisfy that relation I had on the, a couple of slides ago. I went the wrong way. This relationship between their 2 integers, k equals y minus x plus reach, for each arrow. Okay, so that's what we'll say a boundary chart is, and agreeing with our previous definition, we'll say that a boundary chart is realizable if it arises from the boundary algebra of a positroid variety via that recipe I just gave over the past few slides. So a natural question is when are boundary charts realizable? So let me start by saying when boundary charts are not realizable. Let me give a couple of things that certainly cannot happen in a realizable boundary chart. Here's one of them. So I have this arrow here. Its left relation number is 3. I don't have room to put 3 strands to the left. Like I just don't have space to put that many strands to the left of it. So that shouldn't happen. I shouldn't be in a situation where the relation number is so big that I don't have enough room to put the number of strands I want to put on either the left or the right. Something else that can go wrong is something like this. The top arrow tells me I want to have 2 strands which are anti-parallel to it on its left. The bottom arrow only wants to have 1 strand anti-parallel to it on its left. But if I have 2 strands here which are anti-parallel, they're both going to be anti-parallel to the bottom arrow, and this overwhelms it. It has too many strands anti-parallel to it, so that's bad. If you have 2 arrows which are parallel to each other, in this case, the one on top should have the smaller left relation number, and the one on the bottom should have the bigger left relation number. And finally, if I have 2 arrows that cross, they might put different pressures on the same strand of my permutation graph. So the arrow from 5 to 2 wants 1 arrow on its left, 1 strand on its left, which is anti-parallel to it. It's kind of got to go from 1 to 5. And the arrow from 4 to 1 wants 1 strand on its right, which is anti-parallel and spans from its head to its tail. So it's got to be from 1 to 3. And I can't have both in a permutation graph. So if I have arrows that cross, their heads shouldn't be too close together. Otherwise, they might be trying to force 2 arrows to come out of 1 vertex in my permutation graph. 2 strands to come out of 1 vertex. Okay, so these are 3 things that obviously can't happen for reasons that have to do with my construction. But the upshot is that these are the only 3 things that can go wrong. So any boundary chart which avoids those 3 obstructions is actually realizable. And not only that, but we have an explicit combinatorial algorithm which allows us to determine the permutation pi from the realizable boundary chart. And once we, knowing pi is the same thing as knowing the positroid. So really, you can see this as a cryptomorphism for positroids, or loopless and co-loopless positroids. Right, it's a combinatorial construction of a directed graph with some simple combinatorial axioms that allows us to recover positroids and all the relevant information of positroids. So yeah, the tricky thing here is to show that really these are in bijection with positroids. You don't get the same. You don't get the same realizable boundary chart, and you can recover all the data of the positroid from the boundary chart. So yeah, I've got a few more minutes. I'll also say that another thing we did we started to use them towards better understanding the boundary algebra. So recall that we have this description from the work of Jonah and Christina of the boundary algebra as a path algebra modded out by the cancellative closure of some ideal, where the cancellative closure is this kind of like weird operation that I said I don't know what to do with. But we can actually determine a minimal set of generators for this ideal from the data of the boundary chart. So using the boundary chart, we can actually just come up with generators, then we don't have to do this weird cancellation thing, we just have generators for our ideal. And kind of something interesting that pops out of this is that to determine these generators, we need information from the boundary chart, which is kind of very clear in the boundary chart but not in the permutation, and also information that's clear from the permutation but not from the boundary chart. So these two ways of representing our positroid really end up working together to allow us to do something about the boundary algebra. They are, of course, cryptomorphic. They carry the same information, but there's some things which are very clear from the permutation which are not so clear from the boundary chart, and vice versa. So in summary, like what's the takeaway here? Positroids are nice matroids, and one thing that's an easy takeaway for us is that we have a new cryptomorphism. We have a new combinatorial way to think about positroids. Not only that, but our cryptomorphism is not just out of the blue. It gives us some compact presentation of important algebraic relations from certain categorifications that people are interested in. We've also shown that they are an effective tool. By giving us a combinatorial way to think about our boundary algebras, they've actually allowed us to learn more about the boundary algebra, which is not clear from its original definition as a subalgebra of a quotient algebra of a path algebra. So we can actually learn, in this case, the minimal relations. And what we want to do is we want to continue to use them to better understand boundary algebras and their modules, which are complicated, but hopefully having some combinatorial underpinning will allow us to make some progress there with an eye towards the cluster algebra structure on Positroid varieties. And that's it. Thank you very much.
Questions? Peter.
So no is the short answer. They don't play nice with the dimer algebra picture. So when you start doing the quiver and taking dual graphs, you get weird things happening. But you can kind of just throw them in for free, so you're not really losing too much information. Right.
Any other questions?
Do you restrict the class of algebraic structures? Is there some class of algebraic structures that you're restricting when you use these digraphs?
Sorry, can you?
So you've related this sort of digraphical object with positroids, and they're related to some sort of algebraic structure.
Yep.
And is that structure that you're relating to them, this algebraic structure, a subclass of some larger structure that you wouldn't be able to connect to relate to via these digraphs?
So I think if I'm understanding your question right, these cluster algebra structures on Positroid varieties are an instance of cluster algebra structures. So it's a specific cluster structure that exists on Positroid varieties. There's actually could be many. We don't know, or actually I'm not sure if we know if there are others, but this is referring to some specific cluster structure on Positroid varieties. It doesn't tell us anything about cluster structures on other varieties, because we really started from positroids and positroid varieties, and we're doing something very specific to them. It's only going to tell you stuff about the cluster structure on these particular positroid varieties.
Thanks. And would you say that this is that this type of method is fairly restricted to this type of object, or do you see some glimmers of generalizability?
So categorification is a tool which is used more broadly. So the idea of looking at cluster algebras in terms of modules over an algebra has broader application. And as a combinatorialist, I'm certainly in favor of trying to understand these algebras in as combinatorial a way as possible. And I expect that should often be possible, because we're often looking at varieties that somehow come from combinatorics. So short answer, yes. I expect you could have some hope of doing something similar, but there's other steps that have to happen here. There's the categorification piece that has to happen, and kind of determining what algebra we want to look at.
Thanks.
Okay.
Jonathan, so I was wondering, one way of characterizing positroids is as alcove matroid polytopes, and can you see this cryptomorphism at all from the, or in the geometry of the matroid polytope?
We've thought about it a little bit, and it's not obvious to us how to prove that they're equivalent. But yeah, not obviously.
Okay, cool.
I mean, I guess the point is that they are equivalent, of course, but it's just a matter of how to prove it.
Okay. Any other questions? No? Okay. Let's thank our speaker again.